Hey, let's talk about all this business with electron configuration and orbital diagrams. So, beginning with the basics. In order to do configurations and diagrams, you need to know how many electrons can fit into each of the following sublevels. You need to memorize that an S sublevel can hold 2, a P sublevel can hold 6, a D sublevel can hold 10, and an F sublevel can hold 14 electrons each. It's also incredibly important to know that when an element loses electrons, it becomes positive. When an element gains electrons, since electrons are negative, adding negatively charged electrons makes the element into a negative ion, aka an anion. So let's talk about how you'd go about finding these, the full electron configurations. So backing up, there we go. Periodic table of the elements will be necessary. And let me see if I can more or less get these lines so both are in view. How do you find it for beryllium? So there's beryllium right there. How do you find the configuration for this element? And the answer is, I always tell people, it's like a car trip where you're recording everywhere you pass on the way to the destination. There's your home. You always start with the first element. And how do you get to your destination? You need to go from here through here all the way to here. So you have to memorize that this is the S block of the periodic table. S, D, P, and F. So S, D, P, and F. Oops, you can't see that, but F. Down here at this area. So, if beryllium is your destination, see, this is the first period right here. 1s is what we call it. So since there's 2 of them in the 1s block, that's 1s, 2, 2s, 2. This would be 2s1 if we were doing lithium, but 2s2 for beryllium. So 1s2, 2s2. And the way you write that, 1s2, 2s2. This means 2 electrons in the first energy level, 2 electrons in the second energy level, total of 4 electrons. All right, oxygen. 1s2, 2s2, 2p1, 2p2, 2p3, 2p4. So it's going to be 1s2, 2s2, 2p4 because it's the 4th one over. And this is the p block. Yeah, I know, I'm not counting helium as part of the p block. So this is the p block right here. This is 2p, 3p, 4p, 5p, 6p, whatever, you get the idea. So again, 1s2, 2s2, 2p4. That's oxygen. 1s2, 2s2, 2p4. So for potassium ion, the next one is potassium ion. So there's potassium right there. Whenever you're doing an ion, just do the neutral element first and then alter it to be correct. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. This one would end in 4s2, but this is ending in 4s1. So I'm going to actually write the full configuration for neutral potassium to start. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, which we got through here. That's potassium. Now, potassium ion means you have to look at potassium. You see it's here. That means it's a +1 charge. Remember, +1 means losing an electron. So if you lose an electron, you have to remove an electron from here. So 4s1 becomes 4s0, and you're not allowed to write a 0 if it isn't hydrogen. So remove that. So this is correct now for potassium ion. Remove the 1 electron. Now, because it's a ion, you have to put brackets. So there's my brackets and charge, with the new form being 1s2, 2s2, 2p6, 3s2, 3p6, brackets, and a plus charge. All right, now, next thing, bromide ion. We're going to do the same thing. I'm going to find bromine's configuration first and then adjust it to be the bromide ion. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1, 4p2, 4p3, 4p4, 4p5. So 1s2, 2s2. Let's zoom that in so you can see a little better. Let's see. There we go. And maybe I'll do the manual zoom instead of the digital zoom. That's better. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Remember, the 4s2 is always followed by 3d10 when you're crossing across this. So 4s2, this is 3d right here, and then we're on our way over here. So 3d10 and then 4p5. So that's bromine. Now bromide ion, remember, when you look at this, that's a -1 charge. These all are. -1 means adding an electron, because in order to make it negative, you have to add a negatively charged electron. So 4p5 is going to become 4p6 because I added 1 electron. And when I do that, add brackets. There's my bracket. And oops, I almost put the wrong charge in there. It's supposed to be a minus charge. So brackets and charge. Let's do the same thing for nitrogen. Backing out a little bit. Nitrogen, 1s2, 2s2, 2p3. Third one over. So 1s2, 2s2, 2p3. And so with that, we can now do the consideration of how you change it. Looking at the periodic table, nitrogen is a -3 charge, or rather nitride ion is a -3 charge. So -3 charge means adding 3 electrons, and 2p3 becomes 2p6, which means I now add brackets and a 3- charge. And now it's nitride ion. Neon, now notice it doesn't specify it's an ion. Neon is this, a noble gas. So we simply read it off the chart. 1s2, 2s2, 2p6. So one s2, 2s2, 2p6. It's not an ion. No brackets and charge are necessary. That's the answer. Now, abbreviated configurations. This means noble gas configuration. All right, so when we say a noble gas configuration, what that means is you are going to write the last noble gas that occurred prior to the element. So if you look at lithium, which is, let's zoom that out. There we go. Lithium is right here. The last noble gas before lithium is helium. So lithium's noble gas configuration starts with helium. So I'm going to put helium in brackets, and let's zoom that in to make it a little more easily. All right. Okay, so there's helium. Now, after helium, what comes next? You would originally have done, actually I should put this out. Originally you would have done 1s2, 2s1. But we only want to do the portion of the configuration that comes after the helium. So because this is 1s2, you can skip the 1s2 because we just said helium. So because of that, what comes after the helium part, this is 2s1. And so you're right, after helium, it's 2s1. So that's it. That's the abbreviated electron configuration for lithium. Now lead ion with a charge of +4. Ooh, that's a little more involved. All right, let's go through it though. There's lead. The previous noble gas is xenon. So we're only going to do the parts that come after xenon. So I start by writing xenon. And I'm going to start by writing the entire lead configuration for neutral lead and then doing a +4 charge. So the entire configuration for neutral lead after xenon would start here. Now what is this? This is first, second, third, fourth, fifth, sixth. Okay, 6-1 down, so this is a 6s2. 6s2. Now as I pass from 6s2 to here, all this refers to like this thing is located here. All of these are, imagine this is a card, this is a card, this is a card. Imagine you made these into cards and stacked them all right here. The entire stack is right here. So as you pass this way, this is 6s2. This is 4f right here, all the way up to 4f14. So if you're passing over this on the way to lead, you got to pass over this 4f block right here, which means you got to add 4f14. This pen's not writing very well. 4f14. Let me clarify that. So 4f14, and then after 4f, this is the D block. Remember, this is the third, this is the fourth, this is the fifth D block right here. So this is 5D. So 5D, and remember, the D block contains 10, so 5D 10. We're passing over the entire D block in order to get to lead, which is over here. This is in the P block. So this is P1, this is P2, but which P? This is 2P, 3P, 4P, 5P, 6P. So 6P2. 6P2. All right, this is the abbreviated configuration for lead neutral atom, but you want lead with a +4 charge. That means you got to subtract electrons. Caution, you have to take the electrons out of not just the end, but the highest principal quantum numbers. So that means I'm going to ignore number 4 and number 5. I'm going to look at number 6. I need to subtract 4 electrons, which means I go to this energy level 6 first. I'm going to subtract these 2, which means it's actually going to disappear. And then I'm also going to subtract 2 more, and they'll come out of here, which means this actually also disappears, leaving behind just the 4f14, 5d10. So for neatness' sake, I'm going to just wipe this whole thing out and move the xe right over here, because that's what's left after I move 4 electrons to make it a +4 charge. Now, that means it's an ion, so I put another set of brackets and make it +4 charge. And there we have it. And I'll get rid of this extra little distracting mark. Next, let's see. So that's a close-up look at it. Configuration for lead, noble gas, charge of +4. All right, sodium, we're going to do the same thing. Sodium, previous noble gas is neon. So I got neon, and then after neon comes, let's see, 1s2, 2s2, 3s2. So 3s1, because it's the first one. Now sodium is just sodium. It doesn't say sodium ion, so just sodium. So you know what? I leave it like that. Argon. Okay. I know argon is a noble gas, but no, you're not allowed to just write argon in here. That's a no-brain, no-thought answer. So, in order to write a noble gas configuration, the rule applies. I said write the previous noble gas and then everything that comes after. So the previous noble gas is neon, so I put neon in brackets. And then what comes after neon is 3s2, 3p6. Zoom in again. 3s2, 3p6. Next, iodide ion. We'll do the same thing. We'll do iodine and then turn it into iodide. So iodine is right here. Previous noble gas is krypton. All right. So let's put, well, actually, before we do that, let's talk about, I just realized this is going to be an issue with the positive one. So iodine, when it becomes an ion, is a -1. So it goes from 53 to 54 electrons. So it's going to have the same configuration as xenon, which means you do the previous noble gas and then everything it takes to get up to xenon. Fair enough for here. So the previous noble gas is krypton. That's Kr. And now I'm going to do all the electrons necessary to get up to, because adding 1 electron, so iodide has 54 electrons because he added 1 to this to make 54. So I got to make it match this. So that's 1, 2, 3, 4, 5. Okay, so 5s2, 4d10, 5p6. 5s2, 4d10, 5p6. Now it's iodide ion, and then I add brackets and a charge. Barium ion. Okay, the process I talked about here applies here as well. Barium ion. Let's talk about what that's going to look like first. Barium ion has 56 electrons. If you make barium into an ion, barium is a +2. That means subtracting 2 electrons from this. That means 56 minus 2 is 54 electrons. It has the same number of electrons as xenon, which means it has the same configuration as xenon, but no, you're not allowed to write just xenon as your answer, because barium was xenon and then a 6s2. If you subtract 2 electrons, it's now just xenon. No, you're not allowed to write just xenon as your answer. So the previous noble gas before xenon is krypton, so you write krypton to start your answer off. And since barium ion has 54 electrons, because 56 minus 2 is 54, we now need to start with krypton and everything that comes after that in order to get to 54. So that's 1, 2, 3, 4, 5. Okay, 5s2, 4d10, 5p6. Sorry, not 4. 5s2, 4d10, 5p6. And then add extra brackets because it's an ion with a 2+ charge. Let's zoom that in to make it easier to see. By the way, yes, these are the same number of electrons because iodine gains 1 electron to make 54 electrons. Barium loses 2 electrons to make 54 electrons. They both have 54 electrons, therefore they're going to have the same configuration, just different charges because the different charged ions. All right, copper ion with a charge of +1. Copper right here. We're going to follow the pattern. Even though copper is an exception that doesn't quite follow this pattern in real life, we're going to follow what the pattern theoretically should be for its configuration, which is previous noble gas of argon, and then 4s2, 3d1, 2, 3, 4, 5, 6, 7, 8, 9, 3d9, 4s2, 3d9. That's neutral copper. +1 charge means subtract an electron, not from here, but from here because it has the higher principal quantum numbers. So subtract the electron from here. Let's try and do it with this little whiteout. So instead of 4s2, it's now 4s1, 3d9. Leave this alone. And then we add another bracket, and then a charge of +1, and now we have copper ion with a charge of +1. So this is answer here. When subtracting electrons, do you remove them from numbers with the highest or lowest principal quantum numbers? And the answer is from the highest. That's why we did this. Okay, onward. Full orbital diagram. In order to do that, you need to know what remember, this is just a picture of the electron configuration. So helium, look it up on the periodic table, is a 1s2. So you got to turn 1s2 into an actual picture. So you're going to draw a box. This represents the orbital. You put 1s up there to label it. You could also put 1s on the bottom, it doesn't really matter. And then because there's 2 electrons, you represent them with little arrows, one pointing up and one pointing down because they have to have opposite spin. So that's 1s2. Sulfur, its configuration is 1s2, 2s2, 2p1, 2p2, 2p3, or sorry, 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3, 4, so 3p4. So it's 1s2, 2s2, 2p6, 3s2, 3p4. So that's the configuration. Clarify that a little bit. That's a 4. Now let's turn that into a picture. So there's your 1s. There's your 2s. That's your 2p with 3 orbitals that can hold 6 electrons. That's your 3s. That's your 3p. Oops, sorry. There we go. That's your 3p. So that label should be toward the middle. All right, now we go fill it out. 1s2 means 2 arrows. 2s2 means 2 arrows pointing in opposite directions. 2p, since there's 6, we fill it with the arrows going opposite directions. 3s is also full. 3s2. Now 3p4. Remember that none of these boxes get 2 until all have at least 1. So it doesn't matter whether the 1 arrow is pointing up or down, but you don't have 2 arrows until all the boxes have at least 1. So 3p4 is what we said. So 3p1, 3p2, 3p3, 3p4. This is meant to be 2 arrows pointing opposite directions. That's sulfur. Now, neutral iron. Let's find the configuration for that. Oops. Neutral iron. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1, 3d2, 3d3, 3d4, 3d5, 3d6. So let's get in with 3d6. So maybe I'm going to run out of space here, but 1s2, 2s2, 2p6, 3s2, 3p6, 6, 4s2, 3d6. Because it's 1, 2, 3, 4, 5, 6, 1 over. All right, so I got to do all these. 1s, 2s, 2p, 3s, 3p, 4s. This is going to be 3d right here. It's 1, 2, 3, 4. So now it's 5 boxes. All right. I'll zoom that in a little bit. All right, so everything's full until the 3D box. So I can just fill all these with electrons. 2 electrons in each. Oops, there we go. And then since there's 6 here, and this is not the one that's full, remember I got to fill all of them with 1 electron. 1, 2, 3, 4, 5. And then the 6th one doubles up, spinning in the opposite direction as the first one here. All right, so that's 3d6. All right, lithium ion. Let's do the configuration for that first. So that's 1s2, 2s1. But since you subtract 1, it becomes just 1s2 and a plus charge. So that's the configuration. So what you do is you put the box, you put 1s, put your 2, electrons going opposite directions, brackets, charge, lithium ion. Fluorine, you're going to do the same thing. So let's look at what fluorine's going to be. 1s2, 2s2, 2p5. But remember, it's a -1, so you add an electron to make 2p6. It's going to be the same as fluorine. Or sorry, it's going to be the same as neon. So 1s2, 2s2, 2p6 would be the configuration of fluoride ion. So that means you got to do your box for the 1s, you got to do your box for the 2s, and then your boxes, which is to say that's an orbital, these are all orbitals. So that's 2p. And then each one has, that's 2, so it's 1s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6. So there it is. That's the answer. Except brackets and charge. So you can't forget to put brackets and charge. So, last part, abbreviated orbital diagrams. Works the same way as an abbreviated configuration. So let's do neutral sodium. Sodium, the previous one was neon. The previous noble gas is neon, so the configuration would be neon and then a 3s1. So what you would do here is you'd put neon in brackets and then a box, label it 3s, and have just one electron. So you're just turning this into a picture. That's all. Neon, same thing. So neon, it's 1s2, 2s2 off screen, and then 2p6. So 1s2, 2s2, 2p6. The configuration, or sorry, but that of course is the full configuration. The abbreviated configuration is what came before neon, is helium. Helium represents the 1s2, so I get rid of this and put helium. Let's turn that into a picture. Helium. And then there's our 2s. And there's our 2p. And the 2s2. So there's 2 electrons, 2p6. 1, 2, 3, 4, 5, 6. So you can do that because it's full. And that's it. That's your answer. Calcium. Same thing. Calcium, the previous noble gas before calcium is argon. So I'm going to put argon. And then after argon, it's 4s2. So I'm going to put argon, a box, label it 4s, and then 1, 2. There we go, 4s2. Next, bromide ion. So let's, bromine, add 1 electron, makes 36. It's kind of the same configuration as krypton, which means we got to do previous noble gas and everything to get to krypton. So that's argon, and then it comes out to argon, and then 4s2, 3d10, 4p6, because we're going to go all the way to match krypton now to make, because bromide ion has 36 electrons. So 4s2, 3d10, 4p6. 4s2, 3d10, 4p6. These are all full, which is going to make it super quick to draw the orbital diagram. Actually, let's get closer so it's easy to see what I'm doing. So argon, we got 4s, 2, 3, and that's out of the box. There you go, 4. That's 3d, and then 4p. 4s2, 2 opposite electrons. And then this is full, all 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then this is also full. So 1, 2, 3, 4, 5, 6. because this should have brackets and charge, so should this one. It should also have brackets and charge. Iron with a charge of +3. I'm going to do that one down here. It's going to take a little more space. So let's do iron neutral and then adjust it. So iron neutral means argon plus 4s2 3d6. Now, if I want to make it a +3 charge, I got to subtract 3 electrons, which means I need to subtract that, and that just goes away, and then subtract 1 out of here to make it a 5. That way I subtract 1 from here plus these 2 makes 3 electrons. Remember, it comes out of here first, which means it's now Ar 3d5. I guess I should put 3+, but you get the idea. It doesn't really matter. All right, well, let's take this and turn it into a picture. Ar, and then we're gonna leave the 4s, but empty. And then the 3d5. 1, 2, 3, 4. All right, 3d. So leave that empty. Don't erase this. Even though we erased it from here, don't leave it here. And then 1, 2, 3, 4, 5. Brackets, charge. And that's how you do it.